NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, everybody, and a very pleasant good evening to you wherever you may be. My name is Brian White from JPL's Office of Communications and Education, and welcome to the first Von Karman Talk of the 2023 series. It has been a pleasure and an honor to bring these talks to you monthly, and tonight we'll get a chance to talk with one of our incredible robotics engineers at JPL, discussing the process of generating ideas from napkin sketch to prototype to development and testing. Now, before we go any further, I'd like to introduce our questions co-host. For this evening, it's from the Mars Public Engagement team. Please welcome Lindsay McLaurin. Hi, Lindsay.
Hello, Brian, and welcome, everyone. As a reminder, this is your space program, and we want you to be involved in tonight's conversation. So from wherever you're joining us, please use the chat feature to ask questions, and a member of our amazing social media team will pass them along to us. If for some reason you don't see the chat, simply refresh your browser, and it should pop up shortly. Let's get started, Brian.
Thank you very much, Lindsay. All right, folks. Our speaker tonight is in the robotic system group here at NASA JPL, working in mechanical design, machine vision, systems engineering, system architecting, and planetary sample collection. He is currently the co-investigator for the Mars Return Sample Handling Technology Development Task, which is a mouthful, as well as the product delivery manager of the Robotic Transfer Assembly System for the Mars Sample Return Capture Containment and Return System, which we'll talk about this evening. He is actively involved in education worldwide and has taught space exploration in Swahili at an orphanage in Tanzania, lectured on astronomy to children in Costa Rica, Honduras, India, Japan, Holland, Spain, Morocco, and Australia, and organized interactive robotics activities for planetariums in Malaysia and South Korea. He is truly one of our JPL underachievers with all of this. In his free time, he enjoys excavating dinosaur fossils, running marathons, salsa dancing, and scuba diving. Please welcome Paulo Younse. Hi.
Hey, thanks for that great intro, Brian.
Thank you. No, thanks for all that you do. But let's start off, because that's such a great, there's so much that we could talk about. Let's talk about your journey. How did you get to JPL?
I actually got involved in science at a very, very early age. My dad was a geologist, so before I had any comic book collections or video games or baseball cards, I actually had a rock collection when I was a kid. I still remember the first time I brought a show and tell item in the kindergarten. It was a halite crystal, which it's common table salt. But it was the coolest thing for myself and all the kids because it was the rock that you could taste. And I don't know how many geologists out there still lick rocks when they go out into the field. But at the end of the day, we had 28 little kids in kindergarten that were aspiring geologists. So with salty tongues. I wouldn't recommend doing that now, but it was a great way to get involved in science early on. Later on, a couple years later, I got my first telescope, and I still remember going out into the backyard at night and pointing that telescope up into the sky and actually seeing Mars for the first time with my eyes. And that's changed my perspective on Mars. Mars wasn't just a picture in a textbook, but it was something that actually I could see and explore with my own eyes. And it wasn't too long after that NASA started launching and landing rovers on the surface of Mars, exploring Mars, sampling rocks, and learning about the science and history of Mars. And that's kind of what inspired me to want to pursue the career of an engineer, to build these rovers for the first time, eventually take samples of rocks on Mars and bring them back home, add them to our own very own rock collection here on Earth. And that's kind of what motivated me to get a degree in mechanical engineering from Cal Poly, get a master's degree in computer vision, vehicle navigation, and control from the University of Florida, and then more recently pursue a PhD in systems engineering from Colorado State University. So now I'm in the robotic systems group, where I get a chance to every day help develop new technologies that are going to enable these future missions to explore our solar system.
That's incredible. That's one big journey from table salt to what you're doing right now. So let's talk about what you're doing right now and how do you begin? how do these are all just astounding missions? How do you start?
Yeah, great question. So what usually these missions, they start off with a science question, a big question that we're trying to answer. And one of those big questions for the Mars exploration program has always been, is there life on Mars? Can we ever discover evidence that life could have existed on Mars in the past or in the present? And that's been really defining to what our missions have looked like over the last couple of years.
So how do we so you got the big question about, is there life on Mars? How do you even begin to scratch at the surface of answering that question?
So we take that big question and we actually have broken it down into some smaller questions. And those have been, first, is there water on Mars? Can we find evidence of water on Mars? Then was Mars habitable? If we know that there's water, could life have ever existed? And then the third question is, can we find evidence of life on the surface of Mars? And that's kind of formulated our general approach and strategy for Mars explorations for the prior missions. For example, the Mars exploration rovers that we launched in 2003 had the focus of looking for evidence of water on Mars. Follow the water was the theme. And then following that, we had the Mars Science Laboratory Curiosity rover that launched in 2011. And its purpose was to build upon that first question of whether there's water on Mars, and then now look for habitability. So could life have ever existed on Mars? Were the right ingredients for life on Mars in the past? And then that kind of leads us now to the third question. Can we find evidence of life on Mars? And that's the purpose of the Perseverance rover right now. It's looking for evidence of past life on Mars. So, all of these big questions kind of help us really answer that big defining question of, is there life on Mars? And that's kind of what we're doing here with all of these missions put together.
So it feels like each question leads to more questions. When do you actually start getting to answers? When do you start getting to approaching how to answer those questions?
Yeah, that's a great point. So in order to answer these questions, we need to gather evidence on the rocks and on the surface of Mars. So to get that evidence, we need to come up with instruments. So that's the next big thing, coming up with the instruments. And then when we have instruments, we need to figure out, how do we get those instruments to the rocks, to those samples, to gather that evidence. And that's where the engineering comes in. We need to figure out, how do we gather that data for the scientists to help answer that question. And we've done that in the past in a couple different ways. We've sent orbiters and flyby missions to observe Mars from orbit or from afar. So that's called remote science. We also do in situ science, where we can land a rover or a lander on the surface and actually get up close to the rocks on the surface of a planet, and try to gather information that could provide evidence for some of these questions. And then the other approach, which is what we're really interested in now, is we could actually find those samples on the surface of Mars, but bring them back to Earth in terms of sample return, and then use our very own instruments here on Earth to be able to gather information and look for signs of past life on the surface.
Looking for signs of past life on the surface. Okay, that's... we're working our way down from these big questions, these smaller questions. You've now telling us how situ, approach, all these different ways. What do you personally, as one of our robotics engineers, how do you find a way to hook yourself into this, or jump into how to really solve these questions that have been brought to you?
So we come in as robotics engineers and try and address that technology problem of what kind of rover platform can we build to be able to bring these instruments to where we want to gather that data, as well as how do we build manipulators to be able to take those instruments and touch the rock that we want to be able to sample and collect information on, as well as build those tools to be able to gather samples so we can eventually bring them back home. And that's been my focus at JPL, is trying to help build that technology, build that capability into our missions. If you go to the next slide, you can see an example of how we approach that. So This is a example of a prototype rover, a four-wheeled rover that we built to be able to test out uh, opportunities to gather access to rocks, get instruments to the surfaces of planets, and take samples and gather data for some of these scientific investigations, as well as collect samples that we can return back to Earth. So this particular rover had four wheels, had a robotic arm, and on that arm we mounted instruments like a prototype of a micro imager that could take up microscopic images of rocks, a Raman spectrometer that could detect certain molecules on those rocks, for example, organics, as well as scoops, so we can scoop up samples to collect and eventually bring back. This was part of the Arctic Mars Analog Svalbard expedition, which was a expedition where we had a group of scientists and engineers that took their instruments out to this island called Svalbard, which is high up in the Arctic Circle near the North Pole. And it's what we call a Mars analog. It has very similar rocks and minerals and geology and very extreme conditions for life, similar to what we might find on Mars. And excellent location to be able to test out these instruments that are looking for life and get scientists, engineers together to try to practice operating a rover, running through a mock mission and going through the sequence of finding interesting rocks on the surface, driving to those rocks, placing an instrument on the surface with the robotic arm, running science to determine, do we think this piece of rock could hold evidence of past life, and then collecting that sample and storing it away. We lived, if you look in the background, you can actually see the ship, the Lanza, and that's the ship that we lived in for basically 4 weeks, where we sailed around the island, went to different locations, deployed our equipment using helicopters and inflatable boats, and then set up shop and ran experiments all day. Luckily, we were there during the summertime where we had 24-hour daylight, so the sun would just go around the horizon over the course of 24 hours, maybe dip behind those mountains, but it never really got dark. Really, really odd experience, but fantastic environment to be able to test out our systems. And through these types of tests, we gained a lot of confidence that we could test out life detection instruments, deploy them with rovers, make scientific judgments on the samples to determine, is this life? Was this rock created by, generated by life? Was this rock generated by abiotic processes that could simulate evidence of life, but not? As well as, can we collect these samples and store them away so we can test them and bring them back home here on Earth?
So you've already started working on some of these things that you're kind of developing now for sample return in 2020 for a caching system years ago.
Yeah, that's right. Something surprising is what I didn't really learn until I started working at JPL and working on these types of projects is we actually start developing technology for this mission more than 10 years in advance before we even launched. So this was actually in the 2000s, well before we even launched Mars Science Laboratory. But we were already starting thinking about these future missions of how do we develop a rover to look for signs of life, and how do we collect samples. This particular activity helped us demonstrate that we have the technology to be able to do some of that early assessment to get to places of interest where we might have signs of life. We take the next step after doing these first sets of experiments to look at now that we know we can collect samples, we know that we can deploy instruments to look for signs of life. How would we actually collect those samples and put them in metal tubes to actually bring back? If you go to the next slide, you can see the next task. We started looking at in about 2009, 2010. How do we build a system now to take those samples that we've been analyzing and collecting on the surface and store them in tiny little test tubes that we could package and seal up and bring home to Earth as part of Mars sample return? The first one you see on the left, that is the very first prototype of a sample handling, encapsulation, and caching system. designed specifically for Mars sample return to collect samples, store them in tubes, and put them in a little canister that could be brought back to Earth. And surprisingly, it took us about a year to go from concept to first prototype and test. And that's what you're seeing there. And just for scale, you can see an iPhone there. And for anyone that doesn't recognize the model, that's a legitimate Model 3 iPhone back from 2009 that you're looking at. So you can get an idea of the heritage of this technology as well as what the technology looked like back in the day. And you can see on the right side what it turned into. So after we matured that initial concept, we finally built the adaptive caching assembly, which is on the Perseverance rover right now, collecting samples and storing them in tubes.
So besides the technology, like knowing how many updates of an iPhone there have been since then, how do you know that you are making progress?
So we constantly evaluate the technology. We build and test, and along the way, we have something that we call a technology readiness level. So we evaluate our technology, determine is it suitable for flight, and take one step at a time where we start with testing these technologies, these prototypes in a laboratory environment, kind of like what you would see on the left, to make sure everything works, make sure it functions. And then we take the next step of testing these prototypes within a system and take it out to the field into a relevant environment. If you go to the next slide, you can see the next step of the process. We took that caching system prototype, mounted it to one of our Mars technology rovers. This particular rover is the Pluto rover. For some reason, we like to name our rovers after dogs. we have a couple of versions of this technology rover. One of them is called Fido. Another one is called K9. This one is called Pluto. And it has a robotic arm on the end of it and a core, a rotary percussive core, very similar to the core that you see on the rover right now, on the Perseverance rover. We took this rover out into the field. This particular field test site is Mono Lake. It's basically an ancient saline lake that has these calcium carbonates, tufa deposits that you can see in the foreground that we're sampling. And those formations are formed when you get water that seeps through these underwater freshwater springs, and they go into a saline environment and interact with the sediment and cause these formations. And it's very similar to the types of environments that we may want to explore on Mars in some of the ancient lake beds that you see on the surface. So we took this rover out, and we were able to demonstrate for the first time collecting samples out in the field with a coring device, and then storing them in sample tubes using that caching hardware that we had developed. And that kind of moves us one step closer to having a system that we could prove out for a flight system and propose on a mission. What it actually ended up being is it ended up being used for a proposal for the next Mars rover mission. And that time it was the Mars Astrobiology Explorer Cacher MAX-C, which is the rover that later evolved into what we see now as the Mars 2020 Perseverance rover on Mars, doing the same thing, collecting samples, storing them in tubes, and saving those for sample return.
So as you're starting to build these and eventually become great rovers like this, do you start to see what you're missing? What challenges are left once you kind of feel like you've got it mostly done?
When we get to the mission now, the Perseverance mission, we go through a phase that we call a formulation phase. And that first phase of the mission is where we develop all of our high-level requirements and science objectives, as well as identify the key missing technologies. So we get one level deeper into the design, figure out what are we missing, what do we need to develop next in order for this mission to be successful. If you go to the next slide, one of those things that we identified is now we know we can collect samples. We know how to store those samples in tubes. But how do we seal those sample tubes to preserve the science to the best of our ability and bring back the most science that we can without risking any of the characteristics of that sample that could contribute to the science value of that sample? In this nice image, you can see a cross section of sample tube. These are the sample tubes that we're collecting samples from on Mars. And on the far right side, you can see the hermetic seal that plugs off the end of that sample tube. And you think it's, you just need to be able to seal up that sample tube as long as you keep the sample in place. We're great. We're ready to go. We can send those samples back, but there's actually a lot more to it. Not only do we need to think about how can we seal up that tube, but we need to think about how well do we need to seal that tube up. Can we seal up that tube so we don't let any of the sample out, as well as not let one molecule of water that might be in that sample out, or any volatiles, any gases that could escape. And how can we ensure that this seal is gas tight, hermetic? Not only that, we need to really think about the materials that we build this seal and the tube out of. The last thing you want to do is build the sample tube out of a material that's going to react chemically with the sample or contaminate the sample with any trace elements that could mask any particular science that you're using to detect biosignatures or learn about the geology of that sample. Nor do you want to have a tube that is going to magnetically interact with the sample, that could remove any of the paleomagnetic signatures that might help you learn about the past magnetic fields on Mars. And you want to have that seal and that tube be able to be cleaned so we can perfectly clean and sterilize that tube, prevent any contamination from Earth particles or Earth molecules or any organic matter that could confuse the scientists when they're analyzing the sample, and keep it clean. And then kind of lastly, you need this sealed sample tube to be able to survive all the extreme environments that we would see on Mars, extreme environments that we'd see in space on the way back to Earth, as well as all the rocket launches off the surface of Mars, the landing back to Earth, and all the dust and abrasion that you're going to see when you're collecting these samples. So building a seal that meets all those requirements, that is able to hermetically seal the sample tube, even if it's covered in dust and scratched up from the coring process, and then be able to survive day and night for years on Mars, as it can get down to negative 128 degrees Celsius at nighttime, and then up way past higher than room temperature during the daytime if the tube's sitting out in the sun. So you're going to get hot and cold, many, many times. And then you're going to have vibrations and landing shocks, space environments, and you want that seal tube to be able to be, basically bulletproof and foolproof. So surprisingly, it took us years to be able to develop that little seal, and that was one of the key technologies that we really focused our attention on, because it is where the science value is being stored and held, and it's the one thing that we're sending to Mars and trying to bring back to Earth. To give you an idea of what that looked like, if you go to the next slide, you can see some of the early prototypes of the seals that we developed to plug up the top of that tube. And we would go through a process where we would do background research, read papers, learn about the state of the art, state of technology of the field of sealing tubes or sealing anything, as well as build lots of prototypes and do lots of testing and test in all types of conditions and environments. These are some of the earliest examples of seals. Some of them were mechanically activated. Some of them were heat activated using shape membrane alloys. And based on what we learned from this early focused technology development task, we ended up taking the best qualities from these seals and deriving the actual seal that we use on the Mars 2020 sample tubes to seal up the samples. You can see that in the next image, where this is the actual seal, hermetic seal, that we use to plug open the tubes. It's basically a titanium seal that's about the size of a thimble. And it has on the outside a very sharp tooth that's pointed out kind of on the left. And that tooth is covered in about 30 microns of gold, pure gold. And what happens is you press that ferrule that's on the top of the seal down into that seal cup. It expands that tooth and that seal cup about 30, less than a millimeter. And that seal basically impinges and pokes its way into the inside of the tube. And that gold coating just seals up any little cracks or any little scratches, as well as encapsulate any dust. And we're actually able to get a hermetic seal that's helium tight. And that can survive all the environments. A lot of engineering went into the seal. It took us 10 years of prototyping and development. And we actually built probably well over 100 of these seals and tested lots and lots of seal tests and sample tubes to make sure that we can survive all the extreme environments that we would see on Mars, as well as all the environments that we would predict we could see on our way back to Earth.
I just want to just reiterate this. We start with these big ideas and questions. How do you do this? How do you get it back? You think about the gigantic, how big these rovers are. They're really the size of a car. And really, it comes down to this small, tiny little seal in order for us to be able to continue to answer those questions. That's astounding. Do you then get to start to build the real thing? Yeah, go, please. Yeah.
Yeah, we do, and that's the exciting part. A lot of time and effort goes into coming up with the ideas, developing technology, testing it out, iterating on it, and then once you've optimized your design and optimize it to the micron level of detail, you can actually start building them. So if you go to the next slide, this is a photo of us actually building the very first flight hermetic seal in the aseptic clean room at the Jet Propulsion Lab, where we're all covered up in goggles and masks and double gloved, wearing these suits to basically keep the hardware as clean as possible. Trying to keep any particles, any molecules, any types of organic matter, and limit that exposure of that material to these sample tubes and seals. I'm the guy in the far right, the tall guy. You might be able to, I don't know if you can tell by the eyes, but that's me right there. And then we're with our engineers and our technicians and our quality assurance, assembling these seals so we can get them ready to send up on the Rovers rover to Mars.
Very cool. What other type of assembly, what kind of key tech do you have to find kind of to advance this as you keep moving?
So, we as we keep on moving, we need to be able to we need to be able to prove that this works and test it out in an environment that simulates the environment for Mars. And that kind of gives us sense that it gives us confidence that this is going to work, that we're going to be able to bring these samples home. And what you can kind of see in the next image, I think this sums it up nicely, is we developed these technologies over the course of years. And we started off 10 years ago, coming up with the very first prototypes for these sample tubes. And then what you see on the right is what we came up with at the very end, developing all that technology to not just seal up the soup, but drop it off on the surface of Mars. And this is very exciting. This is the first sample tubes that we dropped on Mars over the last few weeks, and it's only been in the last month where we now dropped off, I believe, 8 tubes on the surface of Mars, ready to be picked up. And these is the real thing. Mars sample return is becoming real, and these tubes on the surface of Mars are kind of proving that. And we talked about missions. They start off with a question, and this is a very nice bridge to the next question of how do we bring these samples back? And some of you may be asking that. We have the surface of Mars with these sample tubes. What is the way that we're going to bring these samples back, and how do we answer that question? So what we're doing now is we're actually working. NASA and ESA are working together to answer that question and starting to design the missions to start bringing these samples back home. The way we're going about it is we're developing 2 missions. One of them is a sample retrieval lander that's going to launch in a few years. It's going to have a lander that lands on the surface, and it will have a pair of fetch helicopters that will be able to fly over, grab these sample tubes, bring them back to the lander, as well as have the capability for the Perseverance rover itself to drive back to the lander and drop off sample tubes. And that lander is going to have a rocket called the Mars Ascent Vehicle that's going to launch these samples up into orbit around Mars and put them in orbit within a sample container called the Orbiting Sample Container, or the OSS. And then we have another mission that we're developing called the Earth Return Orbiter mission that's going to launch to Mars orbit, grab this container of samples in Mars orbit and bring it back to Earth, and then spin eject it within an Earth entry system that's going to land back on Earth where we can collect the samples. We actually started thinking about how do we approach that well before we even launched the Mars 2020 rover. And while I was working on the SEALs and working with the team to build the Perseverance rover, I also had a small team that started thinking about that next problem of how do we capture that sample in orbit and bring it back to Earth. Go to the next slide. You can see some of the early development and testing that we were doing in 2018. This is one of the technologies that we were testing out for capturing a orbiting sample in 0G. And it was a really interesting test. We would build this prototype. We would build a prototype, put it into a test bed that you see on the right. And we actually got to go on to a 0G flight where you would be on a jet. It would basically fly up really high at a steep angle up to the sky and then free fall for 20 seconds. And you would get microgravity or 0G that you would be able to test out some things like OS capture and also tracking the OS. And you can see some of those tests on the right side where we had a launcher that would launch an orbiting sample container that would theoretically have those sample tubes. And this particular device was a flux pinning technology where we would have magnets and superconductors to try and capture and levitate that sample container in orbit. You can see those little blinking lights as well too. Those are April tags. We were also testing a vision system to detect these little fiducials, what we call them, these little indicators on the OS and on the hardware to be able to do pose estimation using cameras, as well as do object tracking to track the trajectory of this OS for modeling and simulations that we were doing. One of the other prototypes that we built, if you go to the next slide, is this prototype orbiting sample capture system. You can see it operating on the right side. And basically, it was a giant capture cone. We would have an OS that would simulate going through this capture cone and trigger optical emitter detector pairs. And it would cause this lid to close and this transfer mechanism to swing over with a paddle and slowly push and funnel the OS down into the capture cone into a receptacle where we could later pick up and insert into an Earth entry system. So this was basically one of the very first prototypes that we built for a OS orbiting sample capture system, and it actually set the stage for the architecture of what we're building now to be able to capture this OS in orbit around Mars for these future missions. We're already starting to do the preliminary design and detailed design of these systems to capture the orbiting sample container, and definitely look forward to seeing how that progresses.
Well, we're talking about planning and all of these different small pieces going together. Do you have any idea? Do we have anything that kind of can show what that plan for right now might be?
Yeah, let's take a look. If you go to the next slide, we have a nice animation that's showing what the current plan is for sample return. This is really exciting. So you're seeing a lander. This is the next vehicle, the next mission that we're sending to Mars. It's going to be a lander. There's a 2020 rover collecting samples. And here's what it might look like. We're going to land a lander on the surface of Mars as part of the sample retrieval mission. That lander is going to be able to retrieve these sample tubes, sealed up sample tubes with Martian samples. It'll have a sample transfer system with a robotic arm that will deliver these sample tubes and insert them into this orbiting sample container. And then we're going to close up the top of that container, insert it into a Mars ascent vehicle, and then launch that rocket from the surface of Mars and basically put that sample container up into orbit. And this is really exciting. Never have we launched anything from the surface of Mars. So this is going to be a first. And then following that, we're going to have that orbiting sample container in orbit around Mars, where we'll have another vehicle, this Earth Return Orbiter, which was the system that we were just showing. It's going to capture that orbiting sample container and install it into this Earth entry system. And then that orbiter is going to make its way back to Earth. And then when we get to Earth, we're going to eject that Earth entry system, and it's going to arrive on Earth safe and sound, where we'll be able to collect those samples that we're collecting on Mars and look at them in our laboratories. So yeah, super exciting. And for one, I'm super excited to see these samples return to Earth. I'd be excited to be the first person in that sample receiving facility, seeing the first tube getting opened up. And I would love to see what we get out of that in terms of science.
That's astounding. I mean, landing on Mars is difficult enough, but all these different steps that you're talking about putting together. We've had a lot of amazing comments and questions from our audience tonight. So let's get Lindsay involved here. What are they saying? How's it going out there?
Absolutely. Thank you, Brian, and thank you, Paulo. So, Travis on YouTube asks, what is the likelihood of using more soft robots, and what are the advantages of utilizing soft robots with complex geometrical forms that have the ability to change shape?
That's a great question. I love that question because I'm a robotics engineer. So we love looking at all different ways to use technology and robotics to help us explore places that you can't get to with the current technology. And I think soft robots, basically, they're robots that can change shape, change form and function to be able to contour to terrain or to form shapes that could give the robot more flexibility. And I could see soft robots being used to grip things that are odd shapes, as well as to really help us go to very complex places that wheeled robots can't get to, like steep cliffs or very rocky terrain that a robot with wheels might not be able to easily traverse. So soft robots and the flexibility you can get out of those types of robots can help us interact with the environment a lot more. And I think those types of robots could really help us, not just on Mars, but other places in our solar system that have very treacherous and challenging territory and terrain that we'd want to explore.
Great, thank you. So, Dharmic on LinkedIn asks, how much low level programming knowledge is needed for robotics as opposed to higher level or algorithm based knowledge? And what's the role of high and low level in the development of robotics?
Oh, great question. We actually need both. So we have low level programming that goes into our control of our motors. How do you get a motor to run at a current constant speed or accelerate those motors, as well as react to certain forces and protect ourselves if loads get too high or temperatures are out of the range that we want to run our system at. And then we have a lot of high level commands and high level behaviors that we program in, which are like vehicle navigation, pattern recognition, looking at the environment to be able to make sense of targets that we want to be able to put an instrument onto, as well as do a lot of high level decision making. So we actually have both. So we have teams that develop the low level controllers. We have teams that look at the high level autonomy, and both of those teams really need to work together in order to get a robot to function and be able to perform complex autonomous behaviors.
Great, thank you. Philippe on Facebook would like to know, how do you keep the most sensitive instruments at a stable temperature? And greetings from Mexico.
Hey, thanks a lot. Thanks for joining in, and great question. So we do care about temperature. Everything has a preferred operational temperature. We don't want things to get too cold because they could freeze or break. We don't want them to get too hot either. So we actively monitor those sensor instruments with temperature sensors like PRTs and thermocouples. And as we measure those temperatures, we also put heaters on where if the temperature gets too cold, we'll turn on that heater and bring that temperature back up to a survival temperature that the instruments are specified to survive at. And then sometimes temperatures, certain sensors and certain instruments and certain mechanisms perform best when they're at a high enough or a certain temperature range. So we'll actively warm up our systems to be able to get to the right temperature so we can optimally run them and get the best signal to noise ratio and the best performance out of those instruments. So that's a very good question. Now, I would also point out it goes the other way as well too. Some instruments work really well at cold temperatures. So we actually have active cooling systems to be able to bring the temperature down to the best operational temperature for those those systems and those instruments to operate in.
Thank you. And this question is Donna coming from LinkedIn, and it's on behalf of her 12-year-old son, Josh. Does the dust affect the rover?
Dust does affect a rover in many ways. You might have heard about the solar panels on some of these solar powered rovers, like the Mars exploration rovers and InSight lander. It's having dust on solar panels can affect the amount of energy that we'll get for the sun. So that's something that we worry about when we have the solar powered rovers. Also, dust can get into the bearings and the mechanisms and help to degrade those mechanisms, so they start losing performance, moving a little bit more slower, or even stall. So we take a lot of measures to prevent dust from interacting with our mechanisms by putting all types of seals and bellows around different mechanisms and different devices, and at the locations where things are rotating or sliding. And then we also test. So we actually will build prototypes, throw a bunch of dust on them, and test it out in dusty environments, and running many, many cycles on it to verify that we can still operate underneath dusty conditions.
Great. Caleb on LinkedIn would like to know how many subsystems is a rover broken into, and how many parties are typically involved in the design, validation, and testing of a finalized rover?
Yeah, that's a really good question as well. So we have a rover or a lander, and it's broken down into a couple different subsystems. Some of the main ones are structures and deployables. So we'll have the mechanical structure in the frame of our system. We'll also have avionics, which is all the electronics and the computers. We'll have a software subsystem that captures all of the code and the behavior. We'll have power, so all of the batteries and the power cables and the harness. And then we'll have other things like instruments, various instruments and sampling systems, and those can be all their own subsystems, the various instruments that we bolt onto the lander or rover to be able to do the measurements, and the sampling systems like robotic arms and drills and other mechanisms that be able to do certain things like interact with the environment and collect samples. Those are just a few of them. And we all work together to verify and validate our systems. So once we develop our subsystems, test them out at the subsystem level, we'll bring it all together in what we call assembly, integration, and test, and start assembling those various subsystems together, testing them out, bit by bit to make sure they work as a system. And then we'll kind of do a comprehensive test where we run through the full set of operations with all of our subsystems working together to verify and our overall system meets the requirements and validate that it does the job that we needed to do, that we designed it to do to complete our mission successfully.
Great. And Marie on Facebook asks, greetings from Puerto Rico. How many trials are conducted during the development phase before launch?
How many trials? We usually do a good number of trials at all various levels. And actually, what we usually do is we usually build at least two versions of our systems. We'll build the flight version, the one that we're going to launch and send to Mars or send to wherever planet we're going to, and we'll do at least one test at various levels to test the functionality. Typically, we'll run a test in ambient, so in the laboratory environment at room temperature. But then we'll also test out the system again in a thermal vacuum environment, where we'll bring the temperature down to the coldest temperature that we expect to operate in, bring the pressure down to what simulates whether it be space or Mars pressure, test out our system there. And then also what we do is you typically build an engineering model or another copy of the rover or another copy of the instruments, and then run lots of tests and lots of trials on that copy, particularly on the ground. Once we launch, for example, a rover to Mars, we have another rover here that we built and use here on Earth to be able to test driving on very challenging terrain or test gathering samples before we try it out on Mars, so we can prove that it's going to work and operate as we expect it, to the best confidence that we can before we do it on Mars.
Great. And Paulo, to wrap us up, this is our last question coming from Arseny on LinkedIn. What are the main disciplines should every space robotics engineer be familiar with?
Oh, yeah, that's a great question as well. I would say I think you know about science and math. That's we build our system based off of the latest science data, and we use a lot of math to design our mechanisms and our hardware. Um, Specific fields in engineering that we care about are mechanical engineering for the mechanisms and mechanical systems, electrical engineering to operate all of the sensors and the power of the systems, and then also computer science, programming our robotic systems to be able to perform actions and functions and operations. And those are some of the key things that you think about when you're looking at robotic systems. Also, system engineering is very important, understanding how all of these parts come together. And I would say math and science are important, but also what you need to do is you need to read a lot. So reading is quite important. I have to read a lot of textbooks and manuals and emails to learn and keep up to date with the latest technology. So I know how to apply the latest and greatest of what people have learned. Also, writing is very important. I do a lot of report writing, and I have to publish my findings so everyone can also benefit and learn about the things that we've tried and the things that worked and didn't work. Public speaking is important. Like right now, we're talking and communicating our ideas, selling our ideas so we can promote them. And I would even say physical education. Being fit is also critical because as you saw, some of those tests, we're going out to the field, we're going out to these extreme environments like the Arctic. Sometimes we have to hike up a mile up a mountain with 30 pounds of robot equipment on our back, and you need to be in good shape and have good endurance and stamina to test things out all day in 24-hour sunlight in the Arctic, and then not let that wear you down. So being very well-rounded is very important. Being good at building teams and leading teams is also critical because we don't build a robot all by ourselves. It takes a team of different disciplines and different engineers and scientists and program managers working together to build a robotic system. And then just being having the right personality and the right perseverance to be able to make your way through some of the challenges that we have to face as we invent and test and prototype and prove out some of these new technologies.
Those are a lot of great skills to have, and that is unfortunately all the time that we have for tonight. Folks, please join us next month when we discuss Perseverance. We discuss that rover's 2 years on Mars. I would like to thank our co-host Lindsay and everyone behind the scenes who make these talks possible. It truly does take a team. I would like to thank our excellent speaker, Paulo, for sharing his creativity, his passion, and his curiosity with us. And finally, the biggest thank you of all goes to all of you who join us each and every single month. Stay safe, stay kind, stay curious, and we'll see you in February.